these three principles underlie inferential statistics. First is the idea that often all possible outcomes of a random process exhibit a predictable pattern. We'll demonstrate this in a minute. The second principle is that knowing this pattern can help you decide whether the random process produced a particular set of results. And finally, a set of outcomes that the random process didn't produce must have been produced by some other process. Let's look at each of these in particular, starting with the first one. Often, all possible outcomes of a random process exhibit some predictable pattern. For example, you probably know that flipping a coin, or a penny in particular, is a random thing. If you flip a penny, there are two possible outcomes. First, the penny may land on heads, or the penny may land on tails. And those are the only two outcomes. A penny that lands on a head, well, that's going to be one outcome out of the two possible outcomes, and it's going to happen about half the time. Landing on tails, that's the other half of the possible outcomes. So if you graph those two possible outcomes, they look like this. It's not a very interesting graph, but it does show you at least that the two outcomes occur with equal frequency. Now let's consider a more complicated situation. In particular, let's look at what happens if you flip two pennies, one after another. One possible outcome is to get two heads, a head followed by a head. Another outcome is to get a head followed by a tail, or you could get a tail followed by a head, or you could get two tails. Again, we've covered all the possible outcomes of flipping two pennies. So that first outcome, two heads, that's going to happen that's one of the four possible outcomes. It's going to happen 25% of the time, or a quarter of the time. And the rest of them are also each going to happen a quarter of the time. But if you're looking carefully, you'll notice something interesting. Those two outcomes in the middle, a head and a tail, or a tail and a head, are functionally the same. They produce the same mix of heads and tails, one head and one tail each. So together they account for half of the possible outcomes, and they're essentially identical. If you graph them, you get a slightly more interesting graph. In this case, you see that the two heads or two tail outcomes are half as likely as the outcome with one head and one tail. And you begin to see something like a shape you might recognize as something like a normal distribution or a bell curve. Now, if you randomly flip 10 pennies at the same time, you can produce any of just over 3.6 million unique outcomes. And if you graph them, they look like this. These are graphed in terms of the number of heads and tails they produce. Notice that now you're beginning to see something that definitely looks like a bell curve or a normal distribution. Here's what the 20 quintillion outcomes of randomly flipping 20 pennies looks like when you graph it in terms of the number of heads and tails produced. Again, you see that pattern, that bell curve pattern. And here's what the pattern looks like for randomly flipping 40 pennies. The numbers here are really just too big to write or to talk about. The important thing to see is, again, you see that same characteristic pattern. So the main thing that I want you to see for this segment is that no matter how many pennies you flip, the outcomes, although they're random, exhibit essentially the same pattern, this sort of bell curve pattern where the center is the most common outcome, and that also happens to be the outcome where you have an equal number of heads and tails. Okay, so that's the first principle. Let's have a look at the next one, the idea that knowing this pattern can help you decide whether the random process produced a particular set of results. So let's suppose your particular set of results is a poll of 10 randomly selected city voters, 6 of whom tell you they favor mayoral candidate Smith over his opponent, Jones. Now, we've just seen that it's fairly common to get, say, 6 tails and 4 heads when you flip 10 pennies. Well, if Smith and Jones were tied among all voters, then randomly picking 6 Smith supporters and 4 Jones supporters out of all those possible voters would be similarly common. So a 6-4 split in your poll can't really confidently rule out a tie between Smith and Jones in the election. But if your poll showed 7 Smith supporters and 3 Jones supporters, well, a tie becomes less plausible. and a Smith lead becomes more plausible. After all, a 7-3 split is less likely than a 6-4 split to occur at random, as we've seen in our coin flipping demonstration, when the real split is evenly divided. An 8-2 split for Smith over Jones would make the idea that Smith and Jones are tied even less tenable. And a 9-1 or a 10-0 split for Smith over Jones, well, that would all but rule out a tie, given that such outcomes are extraordinarily rare when the actual split is evenly divided, even with a sample as small as only 10. So in sum, as a particular set of results becomes less consistent with the outcome of a random process, in this case coin flipping, the random process becomes less likely to have caused the results, or to be more precise, a random process that behaves the same way as something like coin flipping would be less likely to have caused the results. Okay, so the third and final principle is this: a set of outcomes that the random process didn't produce must have been produced by some other process. So if Smith and Jones are really tied, it would be exceedingly rare to just happen to get 9 or more Smith supporters in a random sample of 10 city voters. So we can safely rule out randomness, in this case the errors involved in randomly selecting voters for the poll, as the cause of these results. So if randomness didn't cause the results, what did? Well, alternative explanations might include sampling that wasn't really random. It's actually very difficult to do random sampling. You have to ensure that every member of the population that you're sampling from had an exactly equal chance of being included in the sample. Random sampling doesn't mean just willy-nilly picking items or people to include. It means doing it in a very precise and systematic way to guarantee that everybody or everything has an equal chance of being sampled. Another possibility is that your "which candidate do you support" question was flawed in some way. Maybe it used confusing language, or language that was leading people in a certain direction. That would be problematic, and it would perhaps skew the results of your poll. Another possibility is inaccurate reporting of the poll results, or recording of the poll results. Maybe as the data from the poll were being entered, they were entered incorrectly, at least a couple of cases. And there are many, many more of these possible explanations for the way the results came out. But the good news is that careful methodology can rule out, or at least minimize, all of those problems that I've just mentioned. So if you follow careful methodology, and if randomness can't adequately explain the results you got, then there's really only one plausible conclusion left. In this case, Smith appears to be leading Jones in the race for mayor. Fundamentally now, this is how all inferential statistics work. They numerically compare a set of results with the outcomes that you could expect to get at random. And if the results appear sufficiently different from random outcomes, well, that suggests the influence of a non-random process. For example, voters actually favoring one candidate over another. So there's a lot more to inferential statistics than what I've been able to cover in this very brief overview. There's a lot to learn if you're curious. But if what you really want is just some reassurance that inferential statistics are not hocus pocus or mumbo jumbo, then perhaps this quick overview has, at the very least, inspired some faith in inferential statistics as a way of knowing.